Now we're going to talk about energy in an SHM. Now, the first and most important concept is that when we talk about an object in SHM, okay, then there is no loss in mechanical energy, which of course means your PE and your KE. And so when you look at this system over here, right, we know based on what we've seen before that at the equilibrium position, okay, you must have a maximum KE and zero PE. And of course, at your amplitude positions, the opposite is true. And so I can come up with a nice expression for the total energy of an SHM simply by looking at what happens over here. And so since the energy is conserved, at the equilibrium point, PE is zero, and so the total energy must equal to the KE at equilibrium, which is KE max. And so we're going to come up with an expression for this, right, which is of course half m v naught squared, and we've seen before that v naught can be expressed as omega squared amplitude squared. And this is a very, very useful relationship that we can use in SHM, right? The total energy of an object in simple harmonic motion. Now, there are a couple of graphs that we may want to familiar ourselves with. Okay, and first of all, that is, of course, first of all, your energy time graph for an object in SHM. Now, suppose that your object starts off at equilibrium, and that means that your kinetic energy would start off over here on top, and your potential energy will start off at the bottom, zero. So let's use red for potential energy and let's use blue for kinetic energy. Now it can be shown, right? Let's just do KE because KE is easier, which is half mv squared. Remember, this can be written as half m omega squared, right? X naught squared minus x squared. And so you can see sorry, let me just write that again. Right, v in terms of t is not that would be half m omega squared x naught squared cosine squared omega t, or it could be sine, we don't know. But in any case, right, we can see that ke plotted against t will be a cosine square graph, and so it will look something like this. Right, so just going to draw a little bit of this, right, maybe up till here. Okay, and of course, the period coincides right there, right? And your potential energy graph will be almost like a mirror image of this, like so. Okay, and this, of course, is your total energy kept constant. Now, we can also draw the energy displacement graphs. Okay, and in this one, it's a lot easier to stomach. X against E against X. Okay, so let's plot first the two amplitude positions, x naught and minus x naught. Okay, and so in such a situation, TE, of course, again, is constant. KE will be maximum over there, 0 at the two amplitude points. So we join it with a nice little curve like so. That's your KE. And your PE will be the exact opposite of this, like such. PE. And there you have it, energy in SHM.